Hey there! Today, we're diving into something really cool. It's not about just grinding through a math problem. It's more like we're about to crack a secret code. We're going to look at polynomials and find a secret that's been hiding in them all along.
All right, let's get right into it. And to show you what I'm talking about, we're not going to start with some dry, boring lesson. Nope. We're going to start with some magic trick.
You don't need a calculator for this. You don't even have to solve anything. Just watch.
Okay, here's our equation for the day. It's a pretty standard quadratic polynomial, right? Now, somewhere out there, this equation has two solutions, two values for x that make the whole thing work. But they're a secret. We don't know what they are yet.
But what if I told you that I don't need to find those solutions to know something really specific about them? Like, for example, I can tell you exactly what those two secret numbers add up to. It's 5. The sum of those two hidden solutions is 5. I guarantee it.
And I'm not done yet. I can also tell you what you get when you multiply those same two mystery numbers. That product, it's 6. So think about that. Their sum is 5, their product is 6. And I figured all that out just by glancing at the equation. So, how on earth is that possible? Is it some kind of weird magic? Well, no, not really. It's actually something way cooler than magic. It's a beautiful, hidden pattern that's built right into the math. So, let's pull back that curtain. The secret behind this whole trick? It's a really powerful set of rules called Vieta's formulas. You know, you can think of any polynomial as having two sides to it. On one side, you have the coefficients. Those are the numbers you can actually see in the equation. Let's call those the clues. And on the other side, you have the roots. Those are the solutions, the answers you have to work to find. Those are the secrets. And Vieta's formulas? Well, they're the bridge that connects the clues to the secrets. They're a simple set of rules that create this amazing link between the numbers we can see, the coefficients, and the properties of the numbers we can't see, the roots. Okay, so now it's time to break down the trick. I'm going to show you exactly how those formulas worked their magic on that equation we just saw. So, here's our polynomial one more time. Remember the standard form, right? A is whatever's in front of x squared, b is in front of the x, and c is just that constant number hanging out at the end. For our equation, that means a is that invisible 1, b is -5, and c is 6. Simple enough. First up, the sum of the roots. Vieta's formula for this is super simple. All you have to do is take -b and divide it by a. So let's just plug in the numbers we have. -b, well, our b is -5, so -5 is just +5. And our a is 1, so what's 5 divided by 1? It's 5. Boom! Just like that, there's the sum I told you about. No guesswork at all. All right, now for part 2 of the trick, the product. The formula for this one is even easier. It's just c divided by a. Let's do it. Our c is 6, our a is 1, and 6 divided by 1 is, well, it's 6. And there it is, the second number from the trick. See? It's not magic at all. Just this really cool, totally predictable pattern. But here's the thing. This pattern, as cool as it is, isn't just some little party trick for simple equations. It's actually telling us something much deeper about all polynomials. So you're probably wondering, okay, that's neat, but what happens with bigger, more complex equations? What if you have an x cubed or an x to the 4th? Does this elegant little pattern still hold up? And the answer is a big, emphatic yes. It absolutely does. If you look here, you can see how the pattern scales up. For both a quadratic and a cubic, look at that. The sum of the roots is still -b over a. The product formula changes just a little bit. For a cubic, it becomes -d over a. There's actually this really fascinating alternating sign pattern that keeps going for even bigger polynomials. But the main idea, the core concept, stays exactly the same. The coefficients are always holding the secrets to the roots. So, okay, this is a really neat pattern, but why does it actually matter? I mean, why is this considered such a fundamental idea in math? Well, this quote right here really nails it. The true power of these formulas is that they let us understand deep things about an equation without having to go through all the trouble of actually solving it. I mean, think about it. In things like math competitions or when you're doing complex proofs, being able to instantly know something about the solutions is a massive shortcut. It's like being able to understand the whole puzzle without having to solve every single piece. And this idea has been around for a long time. These formulas are named after Francois Vieta, a French mathematician who first figured this out way back in the 16th century, at least for positive roots. Then, about 100 years later, another mathematician, Albert Girard, expanded on it. So yeah, this has been a cornerstone of algebra for more than 400 years. Pretty amazing.
So, in the end, what Vieta's formulas really show us is that even in something as simple as a polynomial, there are these incredible hidden layers of structure and connection just waiting for us to find them. And it kind of makes you wonder, right? What other beautiful secrets are hiding in plain sight in all the numbers that surround us every day?